Welcome to Talk Tensors. We are diving straight into the deep end today because we're looking at a problem that is basically fundamentally breaking MLOps at scale right now.
Oh, absolutely. It's a massive wall everyone is hitting.
Right. And if you are an ML engineer listening to this, you know exactly the headache I'm talking about. You know the deployment nightmare of the standard transfer learning pipeline.
The standard, the monolithic approach.
Yeah, exactly. You take your massive foundation model, say like a T5 for language or a massive vision transformer for images, and you fine-tune it. But you don't just fine-tune it once.
No, you fine-tune it for 50 different downstream tasks.
Right. And suddenly your infrastructure team is just screaming at you because you're no longer hosting one clean, unified model. You are trying to store, manage, and serve 50 distinct monolithic multi-gigabyte checkpoints.
Which is an absolute nightmare for GPU memory.
It destroys your latency with cold starts when you're swapping those models into VRAM. And financially, I mean, let's be real, it is a black hole.
It really is the defining bottleneck of modern AI deployment. You end up with all these highly specialized, incredibly capable, fine-tuned weights, but they are completely siloed. They don't talk to each other. They don't share any representations.
And for the longest time, the community's response to this was just a collective shrug. Like, what else are we supposed to do?
We just accepted the bloat. We knew it was grossly inefficient, but the alternative, which would be training a single massive multitask model entirely from scratch, was just considered computationally toxic.
Right.
So we accepted that if you wanted a model that could do, say, legal document summarization and another one that could do Python code generation, you were paying to host two massive instances.
Which is wild when you think about it, because the dream has always been to somehow magically fuse those multiple fine-tuned models back into a single, highly capable multitask model.
Without doing any additional training. That's the key.
Yes. Just taking the weights we already paid compute for, the ones sitting on our servers, and combining them. But historically, any attempt to just mathematically mash these models together results in, well, it's essentially a localized brain wipe.
Catastrophic forgetting.
Exactly. The models overwrite each other's specialized knowledge, and the performance just falls right off a cliff.
Though in this specific context, it's not caused by sequential training, which is usually how we think of catastrophic forgetting. It's caused by the literal interference of the merged weights in the high-dimensional space.
Right. They literally mathematically sabotage each other. But the landscape is shifting rapidly, and that's our mission today.
Today, we are dissecting a specific, highly viral architectural method that has the entire ML community reconsidering how we handle model endpoints.
It's a three-step procedure, and it operates directly on the model weights that we call pass vectors to isolate the exact knowledge inside these models and fuse them together flawlessly.
It bypasses the interference problem almost entirely, which is, I mean, it's practically magic when you look at the math.
And what makes this so critical for you listening right now is that this isn't just some theoretical white paper playing with toy models. This is a practical, scalable solution that you could theoretically implement in a Python script this afternoon to merge your own isolated models.
Absolutely.
So here's our signposting for this deep dive. We're going to start by looking at the specific math of task vectors and why the traditional multitask learning alternatives are so painful to implement.
Then we're going to expose the hidden saboteurs.
Yes, the saboteurs. These are the exact mathematical phenomena, specifically redundant parameters and sign disagreements that have been quietly ruining our merged models up until now.
And from there, we need to break down the mechanics of the solution itself. The researchers refer to it as trim, elect sign, and merge.
It is remarkably elegant, but obviously we have to scrutinize the benchmarks. We'll look at how it performs against the current heavyweights in model merging across both vision and language modalities.
And even in parameter-efficient setups, which is how most enterprise teams operate anyway.
Right, PEFT methods. And we'll look at how it achieves incredible out-of-domain generalization. Finally, we'll wrap up with the Oracle experiment from the research, which reveals something just fascinating about the sheer importance of weight direction over magnitude.
That part completely blew my mind.
Same. And then we'll transition into our novel notions segment. So jumping right in. If the goal is to have one model do 50 things, the immediate question from a traditional deep learning perspective is, why are we even messing around with merging weights after the fact?
Why not just do multitask learning?
Exactly. Take the base model, stream all 50 datasets into it simultaneously, compute your loss, backpropagate, and build a unified model the old-fashioned way.
Right. And in a purely academic, completely frictionless vacuum, multitask learning is the correct answer.
But not in reality?
Not at all. In the gritty reality of MLOps, it is a logistical and computational nightmare. First, you have the data access problem. To train a true multitask model, you need simultaneous high-throughput access to all of your data sets at the exact same time.
Which never happens.
Never. In enterprise environments, data is heavily siloed. The medical imaging team doesn't share an S3 bucket with the customer service chatbot team. Or, more commonly, data just arrives sequentially over months.
Right. You finish training task A in January, but task B's data set isn't even annotated and ready until March. You literally cannot do simultaneous multitask learning across time.
Exactly. And even if you magically had all the data perfectly curated in one central repository, the compute cost of running back propagation on a multi-billion parameter model across a massive combined data set, it's astronomical.
You're essentially doing a massive pre-training run all over again.
You really are. But honestly, the hardest part isn't even the hardware cost. It's the optimization dynamics. Practitioners refer to multitask data mixing as a dark art for a reason.
Oh, yeah. The gradient interference is brutal.
It is. If you just stream the data blindly, task A might require gradients that push the network in one direction, while task B's gradients push in the exact opposite direction.
They fight each other during the update steps.
Constantly. Furthermore, if you get the sampling ratios wrong, say you have 10 times more data for task A than task B, task A will just completely dominate the loss landscape.
Task B gets drowned out completely.
Exactly. So you have to constantly tweak sampling temperatures, run incredibly expensive validation loops, and just pray you find the perfect equilibrium.
Which brings us to the rise of model merging. If multitask learning is too hard and hosting 100 isolated models is too expensive, we look at the artifacts we already have.
The fine-tuned checkpoints.
Right. We have thousands of these sitting on Hugging Face or in private registries, all derived from the exact same base model architecture. And the foundational concept that makes merging them possible is the task vector.
The task vector is really the fundamental unit of currency in this entire paradigm.
So let's break that down for the listeners. What is it mathematically?
It's actually very simple. When you take a base model and fine-tune it, you start with the initialized pre-trained parameters. Let's represent those as theta init.
Okay, theta init.
After you run your fine-tuning loop on your specific task, you end up with a new set of weights. Let's call those theta FT for fine-tuned. The task vector, which is mathematically denoted as tau, is simply the fine-tuned weights minus the pre-trained weights.
You just subtract theta init from the FT?
That's it.
It's a literal delta. It isolates the exact movement in the high-dimensional parameter space that corresponds to learning that specific downstream task.
Exactly. All the general knowledge, the basic understanding of the English language, or basic visual edge detection, it all cancels out in the subtraction.
Because it was present in both checkpoints.
Right, and you were left with just the specific delta required to summarize a legal brief or recognize a stop sign.
And once you conceptualize fine-tuning not as creating a brand new model, but as adding a specific directional vector to a base model, the possibilities just blow wide open.
Because if you have a task vector for task A and a task vector for task B, the intuitive leap is immediately, what happens if we just add both vectors to the base model?
And this is where the early approaches came in, things like simple averaging or what became formally known in the literature as task arithmetic.
Right.
You just take the vectors, maybe average them out so the magnitudes don't explode into infinity and slap them back onto the base model.
Which is very computationally cheap.
It is. And there were slightly more sophisticated approaches too. I want to touch on Fisher merging briefly because it sounds so great on paper.
Oh, Fisher merging is a mathematically beautiful idea.
With Fisher merging, you don't just average the vectors blindly. You weigh the importance of each parameter using the Fisher information matrix before you combine them.
The theory there is that some parameters are absolutely critical to a task, while others are less important. The Fisher information matrix approximates the second derivative of the loss, the Hessian.
Which is notoriously horrible to compute.
Horrible. But it basically tells you how sharply the loss will spike if you change a specific parameter. So Fisher merging says, let's give more weight in the final average to the parameters that have a high Fisher value.
But practically speaking.
Practically, computing that matrix requires a full forward and backward pass over your training data. It is computationally heavy. It requires access to the original data, which defeat half the purpose of merging. And you have to store these massive diagonal matrices in memory.
And as we're going to see, even with that massive computational overhead, it still fails at scale. because whether you are doing simple averaging or Fisher merging, when you try to combine 3, 5, or 11 models, the performance of the merged model just falls off a cliff.
The simple math of adding vectors together breaks down completely in the high-dimensional space of a deep neural network. The combined model becomes effectively useless at all of the tasks it was supposed to know.
And the reason for this catastrophic drop is the core of our discussion today. It's interference. The vector space of a multi-billion parameter model is so vast and complex that you simply cannot assume linear superposition.
When you add these vectors, they collide.
They really do. The authors of the research isolate two very specific types of mathematical interference that are sabotaging these models. Let's dig into the mechanics of that interference.
Because if we don't understand how the vectors are destroying each other, the ultimate three-step solution won't make any sense.
Exactly. So the paper identifies saboteur number 1 as interference from redundant parameters, essentially the noise floor of the network.
To really grasp this first saboteur, we need to look at the optimization dynamics of deep neural networks during fine-tuning. We know these networks are massively overparameterized. We are talking about billions of connections.
Millions!
When you fine-tune a model on a new task, the backpropagation algorithm is going to update almost every single parameter in the network by at least a tiny fraction.
Because the gradients flow everywhere.
Right, but the literature on things like the lottery ticket hypothesis and model pruning in general tells us that most of those updates aren't strictly necessary.
Only a tiny fraction of the parameters are actually doing the heavy lifting to minimize the loss for that specific task.
Exactly. The vast majority of the weights are just experiencing a random walk. They wiggle a tiny bit during training, but they aren't critical to the final representation.
We have a massive amount of redundancy.
So consider a scenario where you are merging 4 models. Model A was fine-tuned to analyze medical documents. During its training, backprop found that a specific parameter, let's say at layer 12, was highly influential for this task.
It pushed that parameter's value significantly. It has a high magnitude in the task vector.
Right. But then we look at models B, C, and D. Let's say they were fine-tuned on code generation, sentiment analysis, and translation. For those specific tasks, that exact same parameter at layer 12 is completely irrelevant.
It wasn't useful at all.
But because gradients flow everywhere, that parameter still moved a tiny microscopic amount in those 3 models. It's just stochastic noise.
Now, execute a simple average across all 4 models.
You take the crucial high magnitude value from model A. You add the 3 tiny, noisy, near zero values from models B, C, and D. And then because it's an average, you divide the total sum by 4.
You've completely diluted it. You took the exact mathematical value that Model A needed to function, and you slashed it by 75% just to accommodate the noise from the other models.
It's like one person yelling a brilliant idea in a room where 9 people are whispering nonsense.
I love that analogy.
Yeah.
The average volume of the room is just a murmur. The brilliant idea is lost. And if you scale that up to merging 11 models, that crucial parameter is divided by 11. The signal is completely lost in the noise.
That is precisely saboteur 1. The redundant parameter updates from unrelated tasks act as a massive dampening field on the critical parameters of specialized tasks.
But as problematic as dilution is, saboteur 2 is fundamentally more destructive to the geometry of the network.
Oh, it completely tears it apart.
This is interference from sign disagreement, the tug of war.
My immediate thought when reading this as an engineer is that the loss landscape is highly non-convex. There isn't just one right answer.
Right. So when we talk about a task vector, we are talking about movement from the original pre-trained checkpoint. That movement has a magnitude, how far the weight moved, and it has a sign.
Did the weight get larger or did it get smaller? Did it move positive or negative relative to the base model?
And this is where the geometry collapses during merging. Let's isolate a single parameter again. Model A finds that to achieve low loss on its data set, it needs to move that weight in a positive direction. Let's say its task vector value is plus 0.8.
Okay, plus 0.8.
Model B, optimizing for its own data set, finds that it needs to move that exact same weight in a negative direction to minimize its loss. Its task vector value is minus 0.6.
They are perfectly contradicting each other.
Completely. Model A says increase this weight to recognize cats, and Model B says decrease this weight to recognize stop signs.
So what happens during a standard merge?
You average them. You add plus 0.8 and minus 0.6, which gives you plus 0.2. You divide by 2, and the merged task vector assigns a value of plus 0.1 to that parameter.
Which is useless for both of them. Model A needed 0.8, Model B needed minus 0.6.
By averaging conflicting signs, you land right in the middle, which, in the topology of a loss landscape, usually means you've just landed on a massive high-loss ridge.
You're in the worst possible spot. Neither model gets the representation it needs. They've completely canceled each other out.
And this raises a crucial empirical question. How common is this sign disagreement, actually? You might assume that because all these models start from the same pre-trained base, they would generally agree on the broader direction to push weights.
You would hope so. But the researchers analyzed the actual task vectors across dozens of models, and the data is staggering. Sign conflicts are ubiquitous.
Even when you are merging just two models trained on different data sets, a massive percentage of the parameters are fighting each other.
And it scales linearly. When you merge 11 models, you have absolute chaos. The parameters are being pulled in 11 different directions simultaneously.
But wait, I want to pause on that point because there is a detail in the research that completely blew my mind regarding sign conflict.
The same task experiment.
Yes. It doesn't just happen when you merge models trained on different tasks. They found massive sign interference even when they merged different checkpoints that were fine-tuned on the exact same task.
That is one of the most revealing insights into the nature of deep learning optimization I've seen in a while. If you take the exact same base T5 model, and you fine-tune it 10 separate times on the exact same natural language inference data set.
But you just use a different random seed for the data shuffling.
Or a slightly different learning rate. You will get 10 different models that all achieve 95% accuracy. They all master the task perfectly.
But if you look at their task vectors, they will have massive sign disagreements.
Massive.
How is that mathematically possible? If they are learning the exact same task on the exact same data, shouldn't they be pushing the weights in the exact same direction?
It goes back to what you mentioned about the loss landscape being non-convex. There isn't a single global minimum. There are millions of local minima, millions of different valid configurations of weights that solve the problem equally well.
We call this permutation symmetry or mode connectivity.
Exactly. Different training runs will traverse different paths through the loss landscape and settle into different basins. Run A might solve the problem by increasing parameter X and decreasing parameter Y. Run B might solve the exact same problem by decreasing X and increasing Y.
They both work perfectly in isolation.
But if you try to average them, they cancel out, and you end up in that high loss barrier between the two basins.
So even when trying to combine models that essentially know the exact same thing, the tug-of-war destroys the average.
This is why simple averaging is doomed. You cannot just mash these vectors together. The redundant noise dilutes the important signals, and the sign disagreements cancel out the crucial directional movements.
Which brings us to the actual architecture we are discussing today. The researchers looked at this catastrophic interference and designed a specific surgical three-step method to mathematically eliminate these saboteurs.
Without requiring any new training data, that's the crucial part.
Let's walk through the trim, Alexine, and merge pipeline. Step 1, trim.
Right. If the problem is that 80% of these parameters are just noisy whisperers diluting the signal, how do we shut them up safely?
The trimming phase leverages the inherent sparsity of task learning. We process each model's task vector individually.
For a given vector, we look at the absolute magnitude of all the parameter updates. We rank them from largest to smallest.
Then we apply a strict threshold. We only keep the top K% of the parameters. In almost all of their experiments, K is set to 20.
We keep the top 20% of the parameters that move the furthest from the pre-trained base. These are the highly influential parameters that actually encode the new knowledge.
Okay, wait. You're telling me we take a scalpel and just hack off the bottom 80% of the parameter updates? We just strictly reset them to 0.
That's exactly what we do.
My immediate thought as an engineer is that you're going to destroy the intricate, low-magnitude representations in the deeper layers. How is that mathematically safe? Doesn't resetting 80% of the fine-tuning movement completely break the model's performance on its own task?
What's fascinating here is that it doesn't. And this confirms the extreme over-parameterization of these architectures. The research empirically demonstrates that a model operating solely on its top 20% of task vector updates performs almost identically to the fully fine-tuned model.
That is wild.
The bottom 80% of movement was genuinely just stochastic noise from the optimizer. By forcing those updates to 0, we're essentially reverting those specific parameters back to their original pre-trained base values.
So the base model's general knowledge handles those parameters, and we only keep the 20% that drastically shifted to learn the specific task.
It is incredibly elegant.
So step 1, trim, completely defeats Saboteur 1. The room full of whisperers has been silenced. We only have the high magnitude signals left.
But we still have Saboteur 2. We still have the top 20% of parameters from different models potentially fighting each other.
Right. Model A's top 20% might include a plus 0.8 update for a weight, while Model B's top 20% might include a minus 0.6 update for that exact same weight. We need to resolve the sign conflicts.
And this brings us to step 2, elect sign. This is the most critical conceptual leap in the entire architecture.
We have to mathematically terminate the tug-of-war.
Exactly. For every single parameter position across the entire network, we hold an election among the models we want to merge. We look at the trimmed vectors. Some models want to move the parameter in a positive direction, some want to move it negative.
And crucially, because of the trim step, many models now have a value of exactly 0 for this parameter. They are abstaining from the vote.
I love the voting analogy, but how are the votes actually tallied? Because it can't just be one model, one vote.
Right. If 3 models want to move it positive by a tiny fraction, and one model desperately needs to move it negative by a massive amount, a simple majority vote would drown out the strong signal.
You are exactly right. It is not a simple majority. It is a weighted election based on conviction or magnitude.
Ah, okay.
For a specific parameter, we calculate the total positive mass. We sum up the exact magnitudes of all the models that want to move in a positive direction. Then we calculate the total negative mass by summing the absolute magnitudes of all the models that want to move negative.
Whichever direction has the greatest total mass wins the election.
Exactly.
Okay, let's ground this with some numbers for you listening. Let's say we are merging 4 models. For parameter X, model A wants to move plus 0.9. Model B wants to move plus 0.1. Model C wants to move minus 0.6. And Model D was trimmed, so its value is exactly 0.
Okay, so the positive mass is 0.9 plus 0.1, which equals 1.0. The negative mass is just 0.6.
Since 1.0 is greater than 0.6, positive wins the election for parameter X.
Precisely. And the output of this entire second step is a single, unified, network-wide sign vector. For every single parameter out of the billions in the model, we have mathematically agreed upon one and only one direction.
It will either be positive or it will be negative. There is no more conflict. We have created a unified directional map for the merged model.
Which brings us to step 3, disjoint merge, the final assembly pipeline.
We have our trimmed vectors, so the noise is gone. We have our globally elected sign vector, so we know the exact direction every parameter is allowed to move. How do we compute the final parameter values? Because if we just average everything now, aren't we still diluting the signal with the models that voted the wrong way?
That is the exact trap this step avoids. Now that we have the winning sign for a parameter, let's stick with our example where positive 1. We look back at the actual values from our models.
Okay.
During the final merge, we only average the parameter values from the models that voted for the winning sign. We only look at the positive value.
What happens to model C, which desperately wanted to move minus 0.6?
It is entirely excluded from the calculation for that parameter. Its value is dropped completely. And similarly, model D, which was trimmed to 0, is also excluded.
This is why it is explicitly called a disjoint mean.
Yes. We're no longer dividing by the total number of models, n. If we're merging 4 models, but only 2 of them voted for the winning positive direction, we add those 2 positive values together and we divide by 2, not 4.
Wow. That fundamentally changes the math of the merge. If you divide by 4, you are artificially shrinking the magnitude of the update. By only taking the mean of the values that actually align with the elected direction, you preserve the strength of the parameter.
You give the winning models the exact magnitude they asked for without dilution.
Correct. We preserve the specific, high-magnitude knowledge in the universally agreed-upon direction.
Finally, there's one last piece of the equation. We take this perfectly merged task vector, scale it by a single hyperparameter called lambda, and add it back to the original pre-trained base model.
The lambda just controls the overall strength of the task vector application.
And there you have it, a massive, highly capable multitask model created entirely through offline vector arithmetic with 0 data access and 0 additional GPU training required.
It is breathtakingly elegant. Trim the noise, elect a unified direction based on mass, and disjointly merge only the winners.
It really is.
But as anyone who works in ML knows, mathematical elegance on a whiteboard does not always survive contact with reality. So let's heavily scrutinize the testing ground. How did the researchers actually validate this architecture? Because if they just tested this on MNIST or some tiny toy NLP dataset, we wouldn't be dedicating an entire deep dive to it.
Oh, they absolutely threw the gauntlet down on the evaluation scale.
Yeah.
They evaluated this across completely different modalities to prove the architecture isn't just an artifact of text processing.
Let's hear the setups.
For natural language processing, they used the T5 base and T5 large models, classic encoder-decoder transformer architectures. They merged models trained on diverse tasks from the GLE and Super GLU benchmarks, things like sentiment analysis, natural language inference, and sentence completion.
And what about computer vision? Because vision transformers operate on patch embeddings, and their loss landscapes often behave very differently than autoregressive or C2sec language models.
They tested heavily on vision. They used two variants of the CLEP model, specifically the VITB32 and the massive VITL14 visual encoders.
Oh, nice.
They merged checkpoints trained on distinct image classification datasets like SUN397, Stanford CARS, and ResIS45. So we are looking at completely different data distributions and parameter interactions.
But the part of the methodology that really caught my eye was how they handled the fine-tuning setups. Because full model fine-tuning is becoming less common in enterprise environments.
It's too expensive. Most teams are using parameter-efficient fine-tuning, or PEFT.
Exactly. They are using things like LoRa or adapters. If I am just training a tiny 10 megabyte LoRa adapter for a 7 billion parameter model, does this merging technique still work?
They explicitly tested for that. They used a specific PEFT method called IA3 on a massive 3 billion parameter model called T03B.
Now, IA3 is fascinating because unlike full fine-tuning, which updates the weight matrices directly, IA3 injects learn vectors that multiply the inner activations of the transformer layers.
It scales the keys, values, and feed-forward networks.
So the task vector isn't a massive multi-gigabyte delta of the full network. It's just the delta of these tiny multiplicative scaling vectors.
Exactly. And mathematically, merging multiplicative scaling vectors is conceptually very different from merging additive weight updates.
But they made it work.
The researchers proved that you can extract the task vectors from the IA3 parameters, run the exact same trim, elect sign, and merge pipeline, and achieve massive performance gains. It proves the architecture is fundamentally sound, regardless of the underlying modality or the fine-tuning methodology.
Okay, the setup is bulletproof. Diverse modalities, massive scales, full weights, and PEFT adapters. Let's look at the competitors. Who did they put this up against in the ring?
We already discussed simple averaging, which we know fails at scale, and we discussed task arithmetic, which is a very popular lightweight baseline where you just scale the standard merged vector.
But they also put this up against some highly sophisticated, mathematically intense baselines.
They tested against Fisher merging, which we discussed earlier, the method that requires computing the Fisher information matrix. But the most formidable baseline they compared against was regmean.
I want to dig into regmean for a second because the engineering overhead for regmean is insane. Explain what regmean actually does and why beating it is such a massive flex for the team.
Regmean operates on the assumption that simply averaging weights ignores the linear transformations happening between layers. So instead of just averaging weights, regmean attempts to find a merged weight matrix that minimizes the distance between the activations of the merged model and the activations of the individual models.
To do this, it computes a closed-form solution to a massive least squares regression problem.
But to compute the activations, you need the data. To run regmean, you have to run forward passes of your training data through the models. Compute the inner product matrices of the input representations for every single linear layer, store those massive matrices, and then use them to solve the regression problem.
The storage and compute scale linearly with both the model size and the dataset size. It is an incredibly heavy MLOps pipeline.
So we have ties merging, which is literally just vector addition, masking, and sorting, going up against regmean, which requires data access and solving massive regression matrices. Let's look at the hard numbers. How did the elegant three-step pipeline do against these heavyweights for in-domain tasks? Meaning tasks the individual models were explicitly trained to know.
It comprehensively dominated them across the board.
If we look at the NLP setting, merging multiple T5 models, ties merging beat the strongest baselines by an average of 2.3% absolute accuracy.
In the vision setting with the VIT models, it beat the baselines by an average of 1.7%.
Now, to a layperson, 2.3% might not sound like a paradigm shift.
But in the context of these highly saturated benchmarks, where teams spend millions of dollars in compute just to eke out a 0.5% gain, a 2.3% absolute gain without any training is massive.
But where the data gets genuinely astonishing, and this is why this paper went viral, is when you look at the scaling superpower. What happens when we push the number of models from 2 to 11?
The scaling graph tells the entire story. If you evaluate the performance of the merged model as you vary the number of tasks, a stark divergence emerges.
When you merge just 2 tasks, task arithmetic and ties merging perform similarly. They handle the minor interference fine. Simple averaging already suffers a massive 10% performance drop.
But as we climb the ladder, 3 models, 5 models, 8 models.
As you push toward 11 models, the saboteurs completely overwhelm the baselines. The performance of task arithmetic goes into freefall. The sign interference becomes mathematically insurmountable.
But the line on the graph for ties merging stays remarkably flat.
It maintains a normalized accuracy incredibly close to the original isolated models, regardless of how many tasks you stack into the merge.
It proves empirically that isolating and resolving sign conflict is the absolute fundamental requirement for massive multitask scaling.
Okay, so it scales safely, and it dominates on the tasks the models were supposed to learn. But let's be real here. Why do we invest so heavily in multitask models?
If I just wanted a model that did legal summarization perfectly, I'd just use the isolated checkpoint.
The reason we want a unified model is for generalization. We want a model that understands so many different intercepting concepts that it can handle completely unseen problems.
The holy grail of zero-shot transfer. Did they test for out-of-domain capabilities?
They absolutely did. They took the merged T5 models, which were trained on standard tasks like paraphrase identification and natural language inference, and they evaluated them on entirely unseen datasets.
They threw them at Cosmos QA, Social IQA, and Quail datasets, testing complex reading comprehension and common sense reasoning that none of the constituent models had ever seen.
And how did the unified hive mind perform?
On the merged T5 large model, ties merging achieved a massive 4.4% absolute boost over the strongest baseline on these out-of-domain tasks.
4.4% absolute improvement on zero-shot out-of-domain evaluation.
That proves the representations aren't just memorizing their specific datasets. By correctly aligning the signs and merging the high magnitude weights, the models are actually sharing their latent knowledge.
They're synthesizing concepts to become functionally smarter at things they haven't seen. It's a true synergy.
But as impressive as those numbers are, I want to pivot to the part of this paper that will make every MLOps engineer breathe a sigh of relief. They know validation set, Flex.
This cannot be overstated in terms of practical impact. A massive bottleneck for deploying methods like Fisher merging or task arithmetic in the real world is hyperparameter tuning.
Task arithmetic requires you to sweep for the perfect lambda scaling parameter. Fisher requires you to compute gradients over data. To do any of this, you need a held-out validation dataset for every single task you are merging.
And if you are an ML engineer in an enterprise environment, you know how painful that is. Yeah. Sometimes you are handed a model weight by a vendor, and you have zero access to the original training or validation data.
If you don't have the data, Fisher merging breaks down. Task arithmetic has to fly blind, which usually leads to catastrophic drops.
But the ties merging team evaluated this exact blind scenario. They asked, what if we provide a generic, hard-coded recipe that requires absolutely no validation data, no tuning, and no sweeps?
What is the blind recipe?
It is incredibly simple. Trim to keep exactly the top 20% of parameters and set the lambda scaling hyperparameter to exactly 1.0. Just drop those numbers in, run the vector math, and deploy.
And when they tested this blind, untuned recipe against the heavily tuned, data-dependent baselines,
it still utterly dominated them. For example, on the VITB32 vision model, the completely blind recipe showed a staggering 6.6% improvement over the other methods in zero-shot setups.
In fact, ties merging without a validation set significantly outperformed task arithmetic with a validation set by over 2% on the vision models.
That is the ultimate proof of robustness. The architecture naturally aligns the parameter space so perfectly that you don't need to mathematically massage the scaling factor. You just align the signs, drop the noise, and the network hums.
Okay, I want to transition to the underlying implications of this, because anytime a method claims to be the simple, fast, and effective, you have to ask, do we really need all 3 steps?
If I'm trying to optimize my pipeline, can I cut corners?
Did the researchers run ablation studies to prove every piece is load-bearing?
They ran extensive ablations, And the data is unambiguous. The architecture is entirely lean. There is no fat to trim.
If you take the pipeline and you remove step 1, the trim step, meaning you keep all the noisy updates, and just run the election and the disjoint merge, performance drops significantly.
If you remove step 2, the elect step, and just try to merge the trim magnitudes, the sign conflict destroys the model.
And crucially, if you keep trim and elect, but you swap the disjoint merge for a standard average where you divide by the total number of models,
performance takes a massive hit, dropping over 5% in the PEFT settings.
So you cannot cut corners, you need to silence the noise, you need a unified directional sign, and you absolutely must exclude the dissenting models from the final denominator. Every step mathematically protects against a specific failure mode.
But speaking of the signs, the researchers ran a side experiment during their analysis that fundamentally changes how I conceptualize neural network weights.
We have been trained for decades to believe that the magnitude of a weight is the most important thing. How large is the floating point number? But they did an experiment on the fragility of signs that suggests something entirely different.
This is perhaps the most profound theoretical insight in the entire paper. They wanted to isolate the importance of weight direction versus weight magnitude.
So they took a perfectly working, fully fine-tuned model. First, they targeted the bottom 80% of the parameters, the low magnitude ones we discussed earlier.
They went in and randomly flipped their signs. If a weight was plus 0.01, they made it minus 0.01. They multiplied millions of parameters by -1.
They completely inverted the mathematical direction of 80% of the network's updates. What happened to the loss? What happened to the accuracy?
Almost nothing. The model performed perfectly fine. The dashed lines on their evaluation charts barely registered a blip.
Which practically cements the trim hypothesis. That bottom 80% is truly just stochastic noise. The network doesn't even care if it's pointing in the complete opposite direction.
Exactly. But then they ran the inverse experiment. They left the bottom 80% alone, and they targeted just the top 20% of parameters, the high magnitude, critical weights.
They preserved the exact magnitude, the exact size of the weight, but they began randomly flipping their signs.
As they slowly increased the probability of flipping a top parameter sign, the model suffered catastrophic amnesia. The performance completely crashed to random chance.
Wait, think about the implications of that. The network had the exact mathematical scale of the representations it needed. The numbers were the exact right size. But just because they pointed negative instead of positive, the entire cognitive architecture of the network collapsed.
The takeaway here is wild. The actual soul of the learned task, the core representation of the knowledge, isn't necessarily the size of the weights. It is strictly the direction of the biggest weights.
If you get the direction wrong on that top 20%, the knowledge is irrevocably destroyed.
And this theoretical realization leads directly to their final and perhaps most exciting experiment. If getting the direction right is the entire ball game, they designed what they call the Oracle multitask experiment.
Yes, I was hoping we would get to this. Because if we know that getting the correct sign vector, the perfect directional map for every parameter, is the ultimate secret to preserving knowledge, what if we cheated? What if we could peek at the universe's answer key?
The researchers asked exactly that. To get the answer key, they did the incredibly expensive thing. They took the base model and trained it the hard way. A true multitask model trained simultaneously on all 11 datasets using massive compute and perfect data mixing.
They looked at the final optimal parameters of that massive model and extracted its sign vector.
Let's call this the Oracle sign vector. It represents the perfect, mathematically optimal direction for every single parameter to satisfy all 11 tasks simultaneously without conflict.
Okay, so we have the God mode directional map. Then what?
Then they went back to our cheap, isolated individual models. Instead of running step 2, the election process, to try and guess the best signs from the noisy task vectors, they just forced the isolated models to use the Oracle sign vector during the merge.
They said, keep your isolated magnitudes, but strictly use this perfect directional map. What were the results? Lay the numbers on us.
When merging the completely isolated models using nothing but the Oracle sign vector, the cheaply merged model hit 72% accuracy across the benchmarks.
To put that in context, the fully trained, incredibly expensive multitask model, the one that took massive GPU clusters to train, hit 73.1% accuracy.
Wait, I want to make sure the listeners fully grasp this. By simply providing the correct positive or negative direction, the simple mathematical addition of isolated weights almost entirely bridged the gap to the absolute state-of-the-art multitask training.
Yes. It implies something monumental about isolated fine-tuning. It implies that when you fine-tune models in isolation, The magnitudes they learn are already excellent. They are already optimal.
The only thing preventing merged models from achieving true state-of-the-art multitask performance is getting the signs wrong due to interference.
If you fix the signs, you fix the merge.
That is a massive practical takeaway. You don't necessarily need full multitask training anymore. If you can just estimate the correct signs, you can merge individual models and achieve near-SOTA multitask performance for absolute pennies on the compute dollar.
And the researchers proved you don't even need the full oracle to get most of those gains. They showed that by using just a microscopic handful of data, like 32 examples per task, you can train an incredibly lightweight, few-shot multitask model for just a few steps.
Not to learn the task, but purely to figure out the general direction of the gradients. Extract those estimated signs, apply them to the massive individual models during a ties merge, and you get a massive performance boost over standard merging.
It fundamentally changes the paradigm. It turns machine learning from a brute force compute problem where we just throw more GPUs at a massive data set into a clever routing and alignment problem. It is brilliant engineering.
It really is.
Okay, we have covered the massive MLOps predicament, the mathematical saboteurs, the three-step solution, the rigorous benchmarks across vision and language, and the mind-bending oracle secret about weight direction. It is time to transition to my favorite part of the show, where we extrapolate these findings to the bleeding edge.
Let's do it.
Just a quick reminder for our listeners. This segment explores outlandish but plausible ideas inspired by today's tech trajectory and is strictly for entertainment purposes only. Welcome to Novel Notions.
All right, what do you have for us today?
So looking at what ties merging unlocks regarding the power of sparse directional updates, the first idea I want to pitch is taking this technology out of the data center and pushing it to the absolute extreme edge. I call it federated hive mind evolution.
Okay, let's scrutinize this. Federated learning is not a new concept. We already have protocols for training models across decentralized edge devices, like predictive text models on phones. What makes this implementation fundamentally different?
Right now, standard federated learning is bogged down by massive data transmission limits and incredibly complex gradient aggregation. You have to send massive weight updates back and forth, and the central server has to compute complex averages that often fail due to the exact interference we just discussed.
Sure.
But think about what ties merging proves. We don't need gradients. We don't need raw data. All we need is simple math on sparse vectors. Imagine a world where there are millions of smartphones, and every single one contains a small, localized foundation model, maybe a 3 billion parameter model.
Okay, small enough to run locally.
During the day, your phone fine-tunes that model locally based on your specific daily habits, your specific colloquial texts, your unique app usage, your specific coding queries. It becomes a specialized expert on you.
A highly isolated, fine-tuned checkpoint.
Exactly. Now, because this merging method is so lightweight and resolves interference perfectly, your phone never has to send your private data to a central server. It never even has to send the full model. Every night, while your phone is plugged in and connected to Wi-Fi, it simply computes its personal task vector.
It runs step 1, trim.
Yes. It hacks off the bottom 80% of noise, leaving only the highly concentrated 20% of weights that represent what it learned that day. It transmits only that incredibly sparse, trimmed vector to a central hub.
And because it's trimmed to the top 20%, and the base model parameters are known, the actual bandwidth required to transmit that update is a tiny fraction of a normal federated update.
Yep.
It's highly efficient over standard networks.
Exactly. The central hub receives these millions of sparse vectors from around the globe. It does absolutely no training. It doesn't use a single GPU for backpropagation. It just runs step 2, elect sign.
It holds a massive global election across 1 billion task vectors to find the universally agreed upon directional signs.
Then it runs the disjoint merge. By morning, the hub has created a flawless, globally brilliant multitask model containing the synthesized, non-interfering knowledge of 1 billion different daily human experiences.
It pushes the unified weights back down to the phones.
We create a planetary hive mind intelligence, updating every 24 hours, without a single piece of private user data ever leaving a device, and without any central GPU training farm.
That is a fascinating extrapolation. It turns the entire global network of consumer devices into a single asynchronous, privacy-preserving compute cluster. And the critical enabler here is that ties merging natively handles the sign disagreement.
Right.
The fact that one user in Tokyo is learning Japanese syntax while a user in London is learning Python won't cause their edge updates to cancel each other out during the aggregation. The disjoint merge handles the routing perfectly, ensuring both specialized representations survive in the global model. Architecturally, that is highly plausible.
I love it when the math supports the sci-fi. Okay, idea 2. This one goes back to the fragility of sign's experiment, which I am still thinking about. I call it the sign language of the latent space, or sign-only training.
I'm intrigued.
We established empirically that the direction of the top 20% of parameters is vastly more important than the specific magnitude. You can flip the bottom 80% and it doesn't matter. You flip the top 20% and the network dies. So what if we invent a completely new, ultra-efficient training paradigm based entirely on this realization?
You're suggesting we abandon optimizing magnitudes altogether?
Yeah.
That we stop trying to find the exact perfect floating point number for a weight?
Exactly. Calculating complex gradients and applying massive floating point delta updates across billions of parameters is what requires tens of thousands of H100s. It's what consumes gigawatts of power. What if we take a massively pre-trained foundation model and we freeze the magnitudes entirely? They're locked in hardware. We never change the size of the number. We train models only by flipping the signs, making them positive or negative using an incredibly lightweight routing algorithm.
Just flipping the bits.
We already know from the Oracle experiment that applying the correct sign vector alone to isolated magnitudes is enough to bridge the gap to state-of-the-art multitask performance. So instead of backpropagation, as we currently understand it, we treat the neural network as a massive, multidimensional grid of binary switches, +1 or -1. Training ceases to be a massive calculus problem and becomes a purely directional logic puzzle. We just flip sign switches until the loss drops.
That is a wildly provocative thought, and it actually aligns perfectly with some of the bleeding-edge research happening right now with one-bit LLMs, like the BitNet architecture and extreme quantization.
Right.
But taking it to the level of pure sign routing based specifically on the ties merging findings is a brilliant extrapolation. If the magnitude is just the volume of the instrument and the sign is the actual melody being played, maybe we don't need to tune the volume at all, we just need to compose the melody. By restricting optimization strictly to binary sign flips, you could theoretically reduce training compute requirements by orders of magnitude. You could fine-tune massive LLMs on consumer hardware, maybe even a smartwatch, because manipulating binary signs requires almost zero memory bandwidth compared to calculating 16-bit floating point deltas.
Exactly. The melody is in the signs. If we just flip the switches, we unlock the latent knowledge.
It's a really compelling idea.
Well, that gives us a tremendous amount to think about, both theoretically and practically. It is genuinely incredible how a simple mathematical realignment, trimming the noise and holding a democratic election for the directional signs, can completely unlock the hidden potential inside our isolated models and solve one of the biggest bottlenecks in MLOps.
And maybe even change how we think about the nature of learned representations entirely.
Absolutely. If you are dealing with model sprawl in your deployment pipelines right now, I highly encourage you to look at the ties merging framework. Think about what specialized tasks you have sitting in isolated silos and how you might be able to fuse them into a unified endpoint using this exact recipe. Or consider this final provocative thought. If signs hold the actual structural knowledge, could biological neural networks be optimizing strictly for directional activation rather than synaptic strength? Maybe the brain is just running a massive disjoint merge while we sleep.
Now there's a thought to keep you up at night.
Thank you for joining us on this deep dive into the architecture of model merging. Keep questioning the baselines, keep optimizing your pipelines, and we will see you next time on Talk Tensors.